Hello and Namaste everyone. I am Dr. Rimzhim Gupta, a research scientist at Paanduv Applications. I am also an ambassador of Women in 3D Printing from Bareilly chapter. This webinar is organized by Paanduv Applications in association with Women in 3D Printing. And when I am talking about women, I think I have one very special woman in my life who is strong, who is hardworking, who is passionate, and who has an attitude to never give up. I think I imbibed these qualities from her, and she's my mother, and today is her birthday. I just want to wish her all the happiness in her life, and I want to dedicate this webinar to her. Okay, let me just take a sip of my water, and then we can get started with the presentation. Alright, so this webinar is defects in metal 3D printing, and whoever has any question at any point in time, you can type in the chat box and our team will reach out to us. They will answer you right there and then. Let's talk about the flow of the presentation. I will start the presentation from the introduction. What additive manufacturing is, what is the history behind it. I'll go with the challenges of additive manufacturing in current industrial and research scenarios. We will then understand the melt pool dynamics, why it is important, and how we can mitigate the defects by acquiring a stable melt pool. At the last of the presentation, I will talk about how computational modeling can be viable and can be a useful tool to mitigate all these effects. And that's where AM PRAVA comes into the picture. AM PRAVA, FYI, is the computational modeling software that is developed by Paanduv Applications. Let's begin with the introduction. I think with this image, all the Indian audience can relate to this, especially if they are of my age group or 10 plus minus 10 here and there. This guy who is the lead in this particular series, he draws out some drawings on a piece of paper. These are 2D drawings, and then they come into the real 3D object form. So this is just a concept back then, but now it has become the reality, and we will see how it has become the reality. Okay, so in traditional times there were many conventional methods how the manufacturing used to happen. One of them was formative manufacturing, the other one was subtractive manufacturing. In formative manufacturing, the metal used to heat up to a certain range where it used to convert into the molten form. Then this molten liquid, molten metal used to drop into a mold where it will take the shape of the desired product, and then further it will quench to obtain the desired part that we are looking for. In case of subtractive manufacturing, we start with a cube of metal. We start with a block of metal, and then we start subtracting the material out of it by using some sharp cutters, machinery, and we get the desired product, but the waste material in this particular method is huge. Coming on to the additive manufacturing, which is also called Industry 4.0 because it is a digitalized form. In this particular method, the raw material is tiny, very small particles of alloy. These metal particles, when subjected to heat treatment, they are fused together or they are melted in a layer by layer format, and they give rise to the product that you are desiring. The waste in this particular form is comparatively lesser than the subtractive or any other method. Let's understand the timelines, let's understand the history. Although the additive manufacturing started back in 1970s, the stereolithography is a technique that was used in 1970s and 1980s, and the first patent was granted in 1986. Thereafter, in 1988, Another patent for selective laser sintering was granted. Thereafter, in the similar approach, a patent was granted in 1995 for selective laser melting, which is also called LPBF process, which is an advanced form of LPBF process. LPBF is the advanced form of SLM. And in 1999 and up to 2000, the research in biomedical field started progressing, and people started building some prosthetic legs, artificial kidneys, artificial organs, and this was happening in up to 2010, 2011, and now still people are actually exploring that part. But a milestone happened in 2014 where one aviation fuel nozzle was designed, which is the first metal part which was fabricated in 2014. Thereafter, I think we all will know how it is progressing with the computations coming into the picture. Let's understand what 3D printing is. First of all, in 3D printing, you create a 3D geometry in your CAD model, which is a 3D digital model. Now, the metal is subjected. You can take the raw material. These raw materials are solid particles, or these are solid polymers. When they are subjected to certain heat treatment, they are melted and they are fused with each other to give a desired shape. This process is repeated again and again until the part is completed in a computer controlled manner. What are the advantages of additive manufacturing? The shape you see here, the complex part you see here itself is a complex design. Additive manufacturing can easily fabricate this kind of parts because it has a capability to prepare complex and custom shape designs. It reduces the waste comparison to the subtractive manufacturing. It holds the capability to consolidate the assemblies into single part. It holds the ability to improve the existing part properties, and it creates lightweighted materials and lightweighted parts and assemblies. Understanding AM market is very important because we should know where the market is growing. Then and there itself we will be providing the research requirements, the industry requirements, and we will be moving ahead with time. So the growth rate for additive manufacturing market is increasing up to 21.2%, which is a significant number. In 2021, the market was 13.92 billion USD, and in 2027, the market is projected to be around 44.03 billion USD. There are many techniques of additive manufacturing, starting from material jetting, material extrusion, directed energy deposition, wet polymerization, powder bed fusion, and binder jetting. These all processes are significantly different from each other in terms of raw materials which are used, in terms of the energy, how the energy is provided to these systems, and the desired physics behind it. Our focus from this webinar is on laser powder bed fusion, because right now AM PRAVA is focusing on laser powder bed fusion, and it is catering all the needs for metal 3D printing associated with LPBF. LPBF is a process. You can see two chambers right here. One is filled with raw materials, which are the tiny particles. These particles are formed by complex strategies, complex methods such as ball milling, plasma arc technology, and whatnot. So there is a powder scraper at the top of it, and the substrate is at the second chamber. Now with the help of this powder scraper, the first layer of material, raw material, will be spreaded uniformly over the substrate. Then the laser will switch on, and it will hit the powder bed in a custom manner, the scan track that you will provide. In that manner, it will subject the heat to it, and then particles will melt, they will fuse together, and once this process is done, again the powder layer will be spreaded. Again the same process will happen until the part is built. LPBF is a prominent technique which is used in multiple industries, starting from aerospace, automotive, medical, chemical and oil and gas. Okay, this is one hilarious image. I think you all, even the international audience, can relate to it. This is the funniest guy in this show, which is Howard Wolowitz, and he's trying to create his minion from a long period of time, and he's unsuccessful. He sometimes his nose gets longer, sometimes there are some other defects which are happening in the system, but finally he gets this minion, and look at him, how happy he is. Let's talk about the challenges now. Additive manufacturing poses a lot of challenges in terms of research and in terms of industry. This figure I have taken from Deloitte PDF, Additive Manufacturing. If anyone is interested, I can give the link and you can explore the challenges in all the sectors, but here I am mostly focusing about the technical aspect of it and some financial aspect of it. Okay, so if I talk about the cost per part with respect to the complexity of the part, additive manufacturing reduces its cost as the complexity is increasing, but it's opposite in case of conventional manufacturing. The added advantage with additive manufacturing is that it provides you a large window for design and innovation, which is not present in conventional technology. But LPBF process is slow, these processes are slow, mass production is right now it's not feasible, but in upcoming time when research is going on more and more, the people will be using more and more computational aspects of it, it can be feasible. The right hand side plot is a plot between power and scanning speed of the laser, and this shows the parameter range for LPBF for DED. And you can see the parameter window is quite wide because the scale is log scale. Even the LPBF parameter window is not narrow. So when an experimentalist is exploring and trying to optimize these parameters, he has to go through a lot of experimentation, and it can take a lot of his time to actually do the experiments and getting the data out of it. So if I talk about the most prominent and most important processes and parameters, which are process parameters or material properties, these process parameters include laser power, scan speed, scan radius, hatch spacing, layer thickness, gas flow, bed temperature and scanning strategy. Material properties include specific heat, thermal conductivity, viscosity, surface tension, emissivity, absorptivity, melting temperature and whatnot. And if you have more than one phase, those phases will have their own properties as well. So the number of parameters are huge, and the parameter window is also huge. So if I consider, let's say 12 parameters are only important in my case, and if I calculate the experimentation to be done to optimize those parameters will be 2 to the power 12, which is 4096 experiments, and that is a huge number. I think one has to spend a few years to get those numbers, to get those optimized parameters. So apart from that, there is a wastage of costly raw material, because these raw materials are prepared by some of the advanced techniques, and these raw material costs are very high. Recycling of raw material is another challenge that we have faced recently, and even though some of the powder particles are not subjected to direct heat, but the particles here and there are spattering, the liquid is spattering, so somehow they are experiencing the heat, and due to that heat they can change their properties. The machines are very expensive, and the operating cost associated with that is also very expensive, because the power which is consumed by these machines is huge. The manual cost is huge. So, and these were the cost related issues, but apart from that, the standardization of material and alloy is another challenge that AM industry is facing, because commercially 5000 plus alloys are existing, but only just some of them we can use for additive manufacturing. There is very limited material database. Material properties are not available for all the materials, and experimentalists have to do a lot of job to get those material properties, so that even all the community can use that. The parameter window is wide. Defects are there in the part. These defects are arising due to very numerous complexities at the physics scale. There are steep temperature gradients, because the upper layer is experiencing enormous heat, but the layers are not experiencing that kind of heat. So there is huge thermal gradients between those, and the cycle time is large because of the experimentation and time of experimentation involved in those processes. If I talk about specifically for thermal gradients, you can see this plot. The thermal gradients are around 2000 Kelvin per second to 5000 Kelvin per second, and somewhere it is also reported it can be up to 20,000 Kelvin per second as well. These temperature gradients can result into unwanted microstructure development and high thermal stresses in the part. The part can deform and the crack can propagate from these abnormalities. If I specifically talk about recyclability, which industry is experiencing at the moment and they want answer to it. The left hand side image is virgin raw material imaging, and at the right hand side is reused. The blue color shows the FCC phase of particles, but red color shows the BCC. So you see in reused there are some red spots available here, and which show that after heat treatment the phases of the particles are changed, phases of the alloys are changed. So the desired product or the build you wanted to make, it will not give you the same mechanical properties. The bottom images are the microstructures associated to the top ones. Now, quality of raw material is also very important. Raw material has to be exceptionally good. Otherwise, if there are some intrinsic defects in the raw material, intrinsic pores available in the raw material, that can induce the defects in your part as well. So you have to be very careful on that front. Okay, this is one other example, the Westworld. This is a well-known series, although it is not my recommendation, this is one of my colleagues' recommendation. And here they are building the robots which are having the architecture as human, and they are using the 3D printing to mimic that architecture. Here they are using FDM technique. Okay, so once we are done with the challenges for additive manufacturing, we have to understand what's going on, what is the interaction of laser and powder is turning into. So that is where the most physics is happening, and that is where we need to control. Yeah, this image elaborates all of it. The laser is hitting the powder bed particles. The laser is associated with certain heat, and this heat is transferred to these powder particles, Once they reach the melting point, the particle starts melting and converts into liquid. This liquid is having some surface tension associated to that. When the temperatures are high, the surface tension will be low. When the temperatures are low, surface tension will be high. Based on that, there are some effects emerging. Those are called Marangoni effects, which are dependent on temperature, the surface tension dependence on temperature. These are also called thermocapillary effects. Now, when the laser power is very high, or it is higher than when the liquid can reach up to the boiling point, it will start boiling and then the vapor will start generating. The molten liquid will convert into the vapor, and that vapor exerts a pressure on this melt pool, which is called the recoil pressure. Higher the recoil pressure, there is a lot of chances that defect will be generated. But here is what we need to control our melt pool dynamics. These absorption, when the laser is absorbed into the material, they can undergo certain reflection, and those reflections are also called Fresnel reflections. Once the laser is shut off, the liquid will convert itself, it will resolidify, it will convert itself into solid again. So this is the whole process. Here particle dynamics is included, thermal physics dynamics is included, solid mechanics is included. So this consumes a lot of physics which is going on inside it. Let's understand the anatomy of dancing melt pool. The anatomy and the flow of this melt pool is driven by three factors: surface tension, recoil pressure, and Marangoni convection, which is the extended form of surface tension. When the surface tension is high, it restricts the fluid flow and it does not allow it to flow freely. So it creates a lot of droplets, which are also called the balling effect. When the surface tension is low, it enhances the melt pool flowability and it fills the gaps between the particles and forms a uniform layer. Recoil pressure comes into the picture when there is a formation of vapor. When the vapors are formed, it exerts a pressure on the interface on the liquid, and which is a downward force, due to which there can be a flow misorientation, and that drives the flow of the melt pool. Now once the melt pool is created, this can be conduction melt pool, this can be transition melt pool, and this can be keyhole type melt pool. These features depend on the energy you are providing to the laser, through the laser, and the aspect ratio of the melt pool, which is width and the penetration depth. There are some numbers associated to that in the literature, but I think you have to dig in more to get the accurate numbers out of it. These numbers are around 0.8 for conduction mode, 1 for transition mode, and 1.5 for keyhole mode. So one unstable melt pool can give rise to lot of abnormality in the system, which can be related to poor surface finish, porosity defects, balling defects, high residual stresses, undesired microstructure, partially melted powder, and poor bonding between the layers. This is one image, this is one milestone that NASA had achieved when they were in International Space Station in 2014. They sent a 3D printer which was operated on FDM, and they created a tool out of it, and they showed that 3D printers can be operational at microgravity situations also. Let's understand the defects now. These are some beautiful SEM images which are taken by experimentalists, and first image shows the porosity in the system, the second one shows the incomplete fusion between the layers, the third one is showing the cracking in the whole part. The fourth one shows the balling effect due to higher scanning speeds. The fifth and sixth one show the spattering. Now we have to understand how the genesis of pores are happening. Ultimately, there are certain forces which are acting in downward direction. There are certain forces which are acting in upward direction. When these forces are not balanced, that's where the defects are formed. That's where the pores are formed. So that's what is happening here. There is an ambiguity between surface tension and recoil pressure, and the forces are imbalanced. That's where the vapor bubble is subjected into the system. Keyhole pores are generated when excess energy is imparted to the laser and to the melt pool, through the laser to the melt pool. These pores are acting as the stress concentrator and have a negative impact on the material properties. You can see from this image, which I have taken from Nature Communication, and they have shown that the probability of existence of pore at the turning side of the laser is comparatively higher than other places, because that's where the energy is high and the scanning speeds are low. To understand more of the balling, why it happens, as I told you, these defects are associated with the melt pool, but on a deeper sense, these are associated with the surface tension. If the surface tension is higher, the flowability is not enough to let the liquid flow here and there. That's what happens, and it forms a spherical shape. That's what calls the balling. Once the balling is created, there is homogeneity, inhomogeneity imparted into the system. There are irregular shapes, because of which the next layer which is coming in cannot stick to the first layer, and that's where the binding defects come into the picture. The lack of fusion, which is again attributed to melt pool dynamics. Because of the strong temperature gradients among the layers, among the substrate and the top layer, it can lead to complex hydrodynamic flows, and which can lead to spatter formation. These spatter formation generate some irregularities and inhomogeneous fusion, due to which the next layer which is coming in does not play out smooth, and there is a gap between the fused particles and fused layers. One important aspect of defect formation, apart from all the previous statements I made, is effect of temperature. When the parameters are not optimized, parameters have a huge impact on defect formation as well. Here we see the effect of particle size. This is done for tungsten on stainless steel substrate, and you see when the particle size is increased from 5.7 micrometer to 47.53 micrometer, the stability completely goes out of the window. The first image shows that melt pool is stable, but the last image shows that there is a spattering, there is inhomogeneous distribution of liquid here and there. The effect of scan speed is also very important, but these parameters are specific to one single material. You cannot replicate the same set of experiments for other material as well, because the parameter window will completely change. In this case, the scan speed varies from 200 millimeter per second to 2000 millimeter per second, and you see the stability is completely changed. The first one looks smooth, second one is also good, but the last one shows some of the balling effects and some of the inhomogeneities. Similarly, on the left hand side, there is a critical combination of laser power and scanning speed, due to which there are some irregularities, distortions, spattering here and there, unmelted particles, lot of unwanted things. So what is the solution to mitigate the defects? How we can minimize the defects? One solution to it is having a stable melt pool under optimized parameter is just one solution to mitigate the defects. If we are talking about the thermal gradients, if you want to reduce the thermal gradients, which is very important, you have to do preheating. You have to heat up your substrate such that the temperature gradient between the substrate and the top layer does not remain as much as it was before. You have to reduce the cooling rate, and then last but not the least, you have to reduce the recoil pressure. You have to be in the conduction mode in order to minimize the defects, and these can be done by optimizing the parameters. This is another epic series which one must watch. This is also not my recommendation, this is one of my colleagues' recommendation, and we teach us in our trainings also. We give this reference in our trainings also. DEFs, which is related to computational modeling, which includes lot of examples related to quantum computing. I think people who are computationally driven and enthusiasts, they must watch this series. Let's talk about computational modeling and tie the thread together from the previous conversation that we had and now to the computational modeling, how we can minimize the defects. Let's understand a basic distinction between experiments and simulations. There are 4 fields. First is time, second one is cost, accuracy and resources. All 4 are very important. Experiments are slow, these are time consuming. Simulations are faster. Experiments are extremely cost intensive. Simulations are comparatively lower. It is actually much lower. The accuracy for experiments is unbeatable. It is very high, but simulation accuracy can be reasonably high depending upon the physics you are using. If you are using some approximation or not, the accuracy parameters, how well balanced those are. So it can give you a reasonably accurate results also. And resource wise, experiments consume a lot of manual efforts, a lot of power consumption. So this is really resource intensive. But the simulations, if you have a good computational machine, these are very low resource management required. Why computational simulations or multiphysics simulations are required? First, because we want to reduce the cycle time, we want to detect the defects early before the experimentation is done, before the part is created. We need to reduce the waste and we need to improve the economics, and these 4 problems can be addressed at the same time by using multiphysics simulations. Now here is a clear I think some guidelines what will work in simulation and what will not work. So things that will not work, Control C, Control V will definitely not work. Experiments alone will not work because you need to keep up with time also. We don't want to be too late for the upcoming advances. Thermal mechanical analysis only will not work. We need to understand the physics behind the melt pool and the interior of the parts as well. Simplistic CFD models will not work because these escape or these skip a lot of physics in terms of number of phases, in terms of various other physics, vaporization. So simplistic features will not work completely. Empirical analysis alone will not work, and only data driven analysis will not work in this case. The simulation that will work will be an integration of mechanistic modeling with data driven modeling, because you are combining together the best of both the worlds. On the mechanistic modeling side, you are taking advantage in terms of calculating the variables that can affect the structure, properties and defects. It can give you a more deeper insights on the physics side. It can guide your experiments when you have the dominant process conditions. Data-driven modeling will be important when you have a good amount of data and you want to get some meaningful results out of it. You don't want to spend that much of time to run the simulations, CFD simulations or computation modeling simulations, and the data-driven modeling can give you the results just in 5 seconds based on the previous history. It can be experimental data or it can be simulation data. That's where AM-PRAVA comes into picture, because we are in AM-PRAVA combining best of the both worlds. It includes macro scale modeling, which will include the detailed melt pool dynamics and defects. It includes microstructure analysis, which is obsolete in many of the softwares. Particle scale modeling is also very important, and that is included in AM-PRAVA. And this is all coupled with artificial intelligence and part scale modeling. Part scale modeling is soon going to integrate in AM-PRAVA. So AM-PRAVA is accurate, that we can say, because we have done enormous validation on cases related to additive manufacturing LPBF, and we have got accuracy up to 96-97%. The solution AM-PRAVA is highly scalable. You have as many as number of processors and you can use it all by purchasing the licenses of AM-PRAVA. These solutions are customizable because the scientists are sitting right here in our team, and you can ask any problem at any point in time. You can ask for any customization related to your processes at any time. These solutions that we are providing are economical. You can compare it to any other solution in the world and you will not match the economy of this software. Let me just elaborate on how it performs, because I have some sequential animations so that you will understand the LPBF more carefully. This is the first animation which will show you the particle analysis, particle scale modeling. There is a scraper, or you can say spreader, which will spread the particles uniformly in the bed over the substrate. It has removed all the unwanted, all the larger particles which are not giving a uniform spreading of the powder bed. Second one is related to the melt pool dynamics. The laser is moving in positive X direction and you can see the temperature distribution of the melt pool, and the right hand side cross sections show you how well the Marangoni effects are observed here. This is exactly like the dancing melt pool. The third one will give you a clear idea on the defects. Just watch this video very carefully and you will see lot of phenomena which will be happening here. There are 4 phases: solid, molten liquid, the vapor, metal vapor, and the inert gas. The vaporization is happening and how well the liquid is spattering here and there. Yeah, this green color is inert gas. It tries to fill in between when there is nothing in the melt pool, and this animation is done for welding case, and the laser energy is high, which is around 1500 watt. You just see that the spattering is happening. Once the laser will be shut off, the part will start resolidifying, and that's where the defect is captured. Right here, this green spot is the defect. The fourth one is the micro scale analysis. There are 4 scan tracks, 4 layers of laser which is hitting the part. At the bottom right is the temperature distribution, and you can see that how the grains are misorienting themselves, merging together, forming and evolving the microstructure analysis. These structures can be columnar or these can be equiaxed, whichever you have given properties for. I mean, if you want to see whether the propagation will happen or not, and you can change the properties accordingly in your part. This is another example for defect prediction. Just see this video very carefully, and the red color is the liquid, molten liquid, and just now the bubble is captured here, the air bubble is captured. Since it doesn't show the alpha dot liquid, it will just show you the liquid. There are a couple of other examples where we have changed some of the parameters, and you will see all of them are creating a melt pool, and some of them are able to capture the defects. Yeah, how well this has captured this air bubble right here. I'll play this video one more time to just be fascinated about it. Yeah, I think you get the gist. Yeah, this is another 4-phase LPBF simulation where you can see the liquid, the vaporized vapor, you can see right here, and I will show this video one more time. The laser spot is at the circle, which you can see moving with the x direction, positive x direction, and this shows you the temperature distribution. So I would like to talk about the person behind all these recent advancements. He is Rimzhim Gupta. He is the CEO of Paanduv Applications. He is an alumnus of Stanford University, and he is also the lead developer of AM-PRAVA. He has a vision associated with AM-PRAVA which is not limited, and we are going to achieve as soon as possible. So Paanduv aims to upgrade every company's technology to its cutting edge by making computational engineering as an integral part of their workflow. The future of AM-PRAVA, as I said, it's not limited. We are integrating a couple of other modules, everything related to AM additive manufacturing. This includes the wire DED process, powder DED process, FDM process. For wire DED, we are very close. We are soon going to integrate this module in AM-PRAVA. Our vision is that one has nowhere to look for when they want anything related to computational requirements of additive manufacturing. AM-PRAVA will provide you each and every aspect of it. And I believe that in upcoming 5 to 10 years, every industry is going to use computational modeling for their additive manufacturing purposes. So why are you late? I mean, one has to think about these things. If you can go ahead with time, that's the best way to go about it. So Paanduv Applications is using AM-PRAVA, and they are using all this physics which is right here. Laser dynamics, melting, vaporization, radiation, conduction, condensation, convection, particle dynamics, Fresnel reflection, recoil pressure, Fresnel reflection, Marangoni convection, and solidification. There is no physics which is left behind, so these are not the assumption. There is no assumption included in AM-PRAVA. These are all the physics included, physics-based solvers. The features of AM-PRAVA includes it is accurate, scalable, customizable, and economical, and apart from that, this will give you multi-layer simulation, which people often ask us that is your solution provides simulations for more than one layer or not. Spattering is well captured, which you have already seen. It will narrow down your parameter window. It will provide you some limited database also that we have gone through a couple of literature, and then we have accumulated all these properties, and one is always free to use their own properties as well, their own materials as well. So it gives you a gist of a detailed understanding of melt pool dynamics, defects, microstructures, and artificial intelligence. You can contact us at support@paanduv.com. Our contact number is 821-831-7925. I'll show you this video, which is an experimental, nicely shot video by Cavilux. You can see how dynamic this melt pool is, spattering is happening, and I will show you the same effect happening in our simulations. This is the powder bed, and just now this liquid is spattered and gone out of the domain, and this simulation is run for 2 layers. So second layer is also experiencing the same thing. There are some upcoming events in 2023. We are going to organize panel discussion which will have folks from academia and industry to reach up to a certain level of understanding for additive manufacturing. What needs to be done to be prepared for the upcoming challenges of additive manufacturing, and how to address the previous challenges of additive manufacturing as well. We are also going to have PRAVA webinar with updated features and demonstration. We are going to release the newer version, which is 1.5 version of PRAVA soon, and this webinar will have a demonstration of that. Then just after that we will have PRAVA workshop where all the people from industry and academia are welcome to join. With this, I would like to end my presentation with an announcement that there is a link provided in the description box which is related to the demo of this software. If you fill the demo form and reach out to us, submit this form, we will select one out of you to give a free license of PRAVA for 3 months. With this, I have a last words, which is simulations can do wonders if these are accurate. So find its applicability in your organization if you are associated with any sort of additive manufacturing research, and you can see it for yourself, because your productivity will be improved, your cycle time will be improved. You can always write us at support@paanduv.com, and contact number is right here. We are available on all the social media platforms: YouTube, Threads, Twitter, Instagram, LinkedIn, and whatnot. Yeah. So any question about this webinar, you can either write in the chat box, or we can address those questions through support@paanduv.com as well. Okay, thank you everyone for your time.